Quick review from yesterday. Log base 4 of 16. 2. Why? Because 4 needs to be raised to the second power in order for it to equal 16. Okay? Log base 3 of 1/9. -2 because 3 needs to be raised to the -2 power in order for it to equal 1/9. 3 to the +2 power is 9. So 3 to the -2 power is the fraction 1/9. Okay? We'll review logarithms yesterday. Any questions on that? Okay, so we're going to build on that here today. I want us to be able to know what logarithmic graphs look like and how they relate to exponential graphs. So that's what I'm doing here first. Okay? So, we're going to graph this logarithmic function in our notes. Okay? We're going to graph this function. But in order to graph that function, okay, you'd have to kind of plug in numbers for x. You might be able to figure out what good numbers to plug in to get answers and things like that, as long as you pick like multiples or powers of 2 to put here. I mean, you could get your answers, make a little graph, XY table and that sort of thing. But I'm going to relate it back to something you already know, and that's exponential functions. Okay? And then I'm going to show you how they are inverses of each other. From what I've gathered from other people is you guys have not done much with inverses in the past. So that's why I'm going to kind of teach that a little bit here as we go too. All right? Inverse functions are functions that undo one another. Probably the easiest way for me to describe that would be like an x squared function and a square root of x function. Because square roots and squareds undo each other, right? If I take the number 6 and I square it, I get 36. If I take the number 36 and I square root it, I'm back to 6. They undo each other, right? Okay? You don't need to write this down. But this is a function. This is a polynomial function. It's a linear function. Okay? This is a linear function that takes 3 times some number and then adds 2 to get the answer. Do you know what function would undo this one? Or would you know how to find it? The answer that I previously got was not really. Okay, which is okay. To find an inverse function, here's how you do it. You switch the x and the y around, and then you get y by itself. So I subtract 2, and then I divide by 3. This function will undo this function. They are inverses of each other. I'll prove it to you. I'll show how they undo each other. Take a number, let's say 10, easy math. Plug in 10 for x. What do you get for y? 32, right? If you plug in a 10 for x, out comes 32 for y. So in this function, if I plug in a 32 for x, out comes 10 for y. It undoes what this function did. When I plugged in a 10, out came a 32. When I plug in a 32, out comes a 10. We could try other numbers if you want, all right? But they are inverses of each other. The x and y coordinates of this graph will be flipped for this graph. This graph passes through the coordinate 10, 32. This graph passes through the coordinate 32, 10. That will always be true for inverse functions. Now, there's a little bit more in depth that I would like to share about inverse functions, but I want to get back to my logarithms here. Okay? We'll do some more inverse functions, I think, later in the year. But do you kind of understand that a little bit? Yeah. Any questions right now going through your mind? Okay? All right. So, why did I talk about that? Well, in order to graph this, I'm actually going to graph its inverse first and then show you why this graph looks the way it does based on its inverse. Okay? So I'm going to find the inverse of this guy. The inverse of this guy would be x equals log base 2 y. Right? I switch the x and the y around. And then I'm going to change forms from logarithmic form to exponential form. Anybody think they can help me out with that? Two to the x equals y. Yep. Take your base, raise it to the number on the other side of the equal sign, it equals here. So b to the x equals y, 4 to the x equals m, 4 to the second equals 16, 2 to the x equals y. Okay? I can graph this. Okay? Let's make a little table of values. Plug in 0 for x, what do you get for y? 1. 2 to the 0th is 1. Plug in a 1 for x, what do you get for y? Plug in a 2. Plug in a negative 1. 1/2. Plug in a negative 2. 1/4. Okay? So 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. We know what this graph looks like. Exponential growth, right? So this blue graph is y equals 2 to the x. Y equals 2 to the x is the inverse of what I was trying to graph at the beginning. Inverse functions undo each other. So if this graph passes through the coordinate 0, 1, this graph is going to pass through the coordinate 1, 0. This graph passes through the coordinate 1, 2. So this graph is going to pass through the coordinate 2, 1. Because all of the x and y coordinates are going to flip. Because they are inverses of each other. They undo one another.
Will they ever touch?
Okay? These two will not. No. A basic logarithmic graph and its inverse exponential graph will not cross, but I didn't want to say yes because some inverse graphs do hit each other, but these two will not. So I didn't want to say no always, okay? Let me finish the rest of this. So 4, 2, 1/2, negative 1, 1/4, negative 2. Here's what logarithmic graphs look like.
Looks like baseball.
Okay? Here's an exponential graph. Here's a logarithmic graph. They are inverses of each other, and they are perfect reflections. They are perfect reflections over the line y equals x. Because y became x and x became y. That's why they're perfect reflections over the line y equals x. Notice how this graph does not go back into the negatives, right? It kind of gets close to the y-axis but never touches it. Okay? That's a reason, or it's a little bit of a way to show why you'll never be able to do a logarithm of a negative number. I mean, think about it. Let's say this is a negative 2. 2 raised to what power equals negative 2? Can't do it, right? Because when you take 2 and you raise it to a power, you're always going to get a positive answer. You might get a really tiny fraction, but you'll never go negative. You can never get 0 and you can never get negative. So that's why the x value will never be 0, it'll never be negative. The graph doesn't get to that half. Okay? Logarithmic graphs look a lot like this. Okay? Exponentials look like this. They are inverses of each other. They are perfect reflections over the line y equals x. Okay? My goal was to show you what a logarithmic graph looks like based on what we already kind of knew exponential graphs look like. And it also allowed me to show you what inverse functions kind of are all about. I'm just scratching the surface on inverse functions, but that was just kind of, I wanted to include that in there a little bit. How are we doing so far? Relating logarithmic graphs to their inverse exponential graphs. We've kind of followed things, yeah.
So, do you think it's easier if we always put the logarithmic or whatever into your other equation? And
Yeah.
then like flip the x and y? Is that an easier way to find it?
Yeah, I'm not going to have you do a ton of graphing, but yeah, it might be, when you see this, it might be good to think this, because this is the inverse of this.
Well, wouldn't you flip them?
Well, yeah. I'll show my work.
Well, you just-
I just skipped a step. So I did. So you flip them like you said, right?
Yeah.
And then you go 5 to the x equals y, which would give me that. I just skipped that middle step. But, which is not a big deal. I was wanting to show you how, I want to talk about how these are inverse functions. So if you see this, you can kind of think, oh, it's inverse function. We'll still have the base of 5. It'll just be y. It'll be an exponential function. If this was a 4, this would be a 4. These are inverses of each other. So if you see this, you can kind of think this.
Yeah.
Think about what this graph would look like. Think about the coordinates that this graph would pass through. Whatever coordinates this graph passes through, flip them. That'll be the coordinates that that graph passes through. Okay? Good. Any other questions? Okay. I think that knowledge will help you with the third exercise in your logarithm unit. Okay? I think that knowledge should help you with the third exercise. Take about 10 minutes and try to do that. Okay? If you're already done, this is where I'm going next. I'm going to teach it. All right? But if you want to try and work ahead, you potentially can.